Okay, awesome. Is there a better way to do this if not PDF? Probably just
I don't know. It
okay.
might be a different view setting
Okay.
than having like page by page.
Yeah. Right here. That's not it. Presentation mode. There we go. All right. This one. Oh, there it is. All right. So just wait till 5
Yeah,
or
maybe 2 minutes, like 5.
yeah.
Um, you also could probably try to hide
Oh,
the cookie.
yeah. Um, I yeah, that's one thing. Uh, okay, nice.
If you're taking 225,
I have not taken 225. I took, well, okay. Freshman year, I was the CS major at the University of Wisconsin, and there they have CS 300, which comes here as 128 credit, but they include data structures within that. So I kind of, uh, I took and dropped the fourth MCB 432, which is about informatics class. The content was interesting, but I do not recommend the professor for a variety of reasons.
what do we
Um, he's a nice guy and clearly knows his stuff, but his directions are very poor and he doesn't grade in a timely manner. Like for this next project that was coming up before I dropped it, he wanted us to make an HTML scatter plot that he could interact with. The prerequisite to this class is biochemistry, and that did not teach us HTML. And I'm lucky because I knew HTML from learning it myself, but he never taught a lot of the stuff that he expected. So yeah, yeah. I think there's like 10% of the class remaining so far. So
no record.
it made the board easier to see. Like week 4, I was like, wow, I have a clear view of this lecture. Yeah. Yeah, but other than that, I don't have much math or CS experience. It's not genetic, surprisingly enough.
I was just asking because like the Burroughs-Wheeler transform,
Yeah, yeah, yeah.
I saw in 225 honors.
Oh, really?
Yeah.
Ooh.
I was 225 honors. How was that? It was pretty so. Yeah.
Temper your expectations on the whole. How much does he know the math? I tried my best. That's kind of the reason I'm giving this presentation, though. I think
Yeah.
bioinformatics is lacking in people who actually know how to code. It's a lot of people like me who are bio majors and have taken 2 CS classes. And I think learning the bio is the easy part, but maybe it's think we can get started. Hello, my name is Arian Day. Not the usual type of presenter, I think, because I am a molecular and cellular biology major with a slight interest in computers. So, first of all, I want to start with the clicker working.
You might have to like click on the.
Oh, yeah, I think that was, yeah, okay, there we go. All right. So, quick outline, we'll get to all of it. The presentation will be too much. I focus on breadth, not depth. This is not all the bioinformatics has to offer. There's computational chemistry. You can do cool stuff with simulations and a lot of other stuff that I just don't know. You kind of pick something and just you can go as deep as you want into it, especially if you have the CF background you need. And this is all I've only worked on genomics and image processing, both at an undergrad level. So again, I'm not gonna pretend I know everything, but I think what I know is interesting to you guys. So what is bioinformatics? So I want to start this off with a fun quote. Bioinformatics is an attempt to make molecular biology relevant to reality. All the molecular biologists devoid of skills beyond those of a laboratory technician cried out for the mathematicians and programmers to magically extract science from their mountain of shitty results. This is kind of my experience firsthand as a bioinformatician, and I want to say that's kind of the fun part because biology is messy. Biology has shitty results. Biology, when you picture it, it's a bunch of cells on a plate. It is kind of like that. And a lot of things can happen. I'd recommend reading more by Frederick J. Ross. He's the type of guy who makes really interesting writing, but it sounds like a huge pain in the ass to work with, which is, I think, my favorite type of person you'd find on Twitter or running a Substack. And this is something else I want to add. The ones that know coding usually fear the math. Molecular biologists, for some reason, are scared of computers. They have this phobia. If you can program and you're looking for an internship, for instance, I would recommend looking into biology ones and emphasizing that you know how to program. This has gotten me a job the last 2 summers. Literally just, I think the hiring process for my last internship, he said, quote, I had the stack of resumes as a biologist. I control F and I typed in the word Java and your resume came up, so I hired you. It's a very unique field. You can do a lot of different things. And it's a lot of people like me who have taken up to CS 128, plus I technically a little bit of 225, and then a bunch of biology paperwork, which is fun, but a lot of times not really necessary to do bioinformatics. So don't let that stop you. I think the field will benefit from your perspective. Code and bioinformatics is a research grade, which is poorly implemented, poorly documented, often not available. The next publication I'm working on, a lot of it uses MATLAB code that my PI wrote as a postdoc, and he's not just still doesn't really know how GitHub works. So I think more classically trained programmers would benefit a lot from adding to the field. So what are some cool algorithms in genomics that I want to show you? One of them is the Smith-Waterman algorithm. Who cares about this algorithm and why? You want to determine similar regions in nucleic acid and protein sequences. If you ever went on 23andMe and they say you're like 47% Italian, this is kind of how it works. It's basically just matching nucleic acid and protein sequences. So if you've ever seen one of these in your bio classes, even in high school, you see a bunch of bases lining up. You always put this in an NCBI blast or a computer program that does it. This is one of the ways and partly how it does it. This is not everything. The NCBI blast, this is something I've used a lot in research, and this is a small part of how it works. It's a lot more complicated than this. Obviously, it's a big program, but this is going to give you some good context. So here's the formula. So at a particular position, which you'll see later what I mean by position, there's either a match or mismatch of the bases. So is it an A to an A when you're comparing two sequences at like spot 4 or at frame 5? Is it a C to an A? That's match or mismatch. So a gap in sequence A or sequence B, basically if you have to adjust by going up or down or sideways. And then local alignment, this is the important part that makes it different from something called Needleman-Wunsch, where it doesn't allow negative scores. I'll explain all this later, and I think it's best explained through an example. So matching is, again, if you have for one sequence and another sequence, if they're like A to A, you'd have a positive score that's good, so that's a +1. If it doesn't match, there's a penalty, And so you always want to move diagonally. If you move to the left or right or up or down, that's what we call a gap penalty. So it kind of works like this. You do this kind of Sudoku looking thing, and you have all these bases at the top and to the right. So this is 0.7. Why is this 0.7? So first, before, let's pretend this was blank. How do they get to 0.7? You'd have 1, 0, and 1 because it works diagonally downwards. So you'd only look at these three values. So if you start at this one, you'd be like, oh, okay, it's a mismatch on the next one, GA, that would be 0.7. Except remember, you're not going diagonally down. So you'd also have to introduce a gap penalty. If you, same thing if you go from here, but instead you're starting at 0. You can't have a negative score, which is what makes us different from Needleman-Wunsch. So that would be 0, so you wouldn't use that. But see, you have 1, you move here. You didn't get a gap penalty because you moved diagonally, but there's a mismatch. So that's minus 0.3. So why would you care about gap penalties? Gap penalties are basically saying is kind of like an offset. Sometimes there's inserted or deleted frames, not always two sequences you're comparing are the exact same amount. So you'd have to compensate by introducing gap penalties. So that's the utility. So the longer the gap, greater the penalty. Stuff that's super long versus stuff that's super short is going to be very different versus two sequences that are similar lengths generally. So if you do this out long enough, you start to get a table where you can see how much stuff matches and you can kind of build and get an idea of how similar two sequences are. Thankfully, we have computers because I had to do this for an assignment in MCB 432, and this is a big pain in the ass to do by hand. So why would you reset the score to 0? Why do I keep talking about Needleman-Wunsch and why this is different? This is usually the more preferred algorithm because it resets the score to 0. Let's say you didn't reset the score to 0. You let it rack up those negative gap penalties. If at the beginning you have something where you have to introduce a lot of gap penalties, even if the rest of it matches up perfectly, it's just going to keep being negative because remember, you're taking the value, you're taking it from referencing previous values. It's not new cases every time. So you might just have a bunch of negatives, and then it'll make it look like even if you have like at the middle is similar, if the beginning's not similar, it'll look like the whole thing's not similar, which is useful if you're doing global alignment, if you're comparing the whole thing 1-to-1, but that's not really how biology works, and you're rarely doing that. So we prefer this. So global alignment, when you're trying to align the whole sequence, so you can get a lot of negative scores, versus local alignments, if you're looking at very similar subsections, if you reset the score to 0, it's more as if you're looking at local sequences and you're restarting the alignment. You're making sure that past failures to match don't affect it later down the line. So if you, that's more of what I was saying, where you don't want something earlier on messing up the score for the rest of it as you keep going. So you only want to look at the well-aligned sequence because a lot of the times, if you're looking at comparing two species, let's say only the 16 sRNA segment matches, but that's what you're looking for. This will make sure you catch that and not that it gets messed up by being a completely different species with a whole host of other different genes. So Burrows-Wheeler transform, as you said, yourself.
Just about the last one.
Yeah, sure.
I was wondering, why choose 1/3 for the gap penalty?
Oh, that's another thing I probably should have mentioned. It's kind of arbitrary. It kind of just depends on what algorithm you're using. If you look up examples, you see a whole bunch of different tables. The reason I use this one is because this is the one we were given in MCB 432. I don't know where he got it from. There's no set scoring penalty or gap penalty. It kind of depends on the problem you're looking at. There's a lot of biology factors. But as an exercise, it kind of doesn't matter. There's more the fact that you're getting XYZ in terms of gaps. Like as long as you're subtracting in terms of gaps and you get a general point.
So for the result, is it the more positive match?
Yeah, for a sequence. I think it's O of n squared because you're comparing like two sequences like this. But the thing is, this is not usually like the whole algorithm. I don't want to call this. It is technically an algorithm, and I think if you look at the original literature, that is the runtime. But there's a lot more involved to this, so I don't want to say like, oh, sequence matching is something you can do in O and F squared. It's a bit more complicated than that. So as well. Burrow-Wheeler transform. is something apparently that you go over in CS225 honors. I didn't know that because I've never taken a CS course here.
I don't know. That's like iffy. I don't know if that was in the same concept.
Okay, well,
that's what it was like.
So, but some of you might be familiar, so that'll make this a little bit more easy to understand. So, what is Burrow-Wheeler transform? It's a data transformation algorithm. If you ask ChatGPT what is Burrow-Wheeler transform, it's going to pretend that it's a compression algorithm. It doesn't really do the compression. It makes the data easier to compress, but is not a data compression algorithm. Two separate things. You'll use it in data compression algorithms, but I think it's an important distinction to note because if you Google this, some things will say it's a data compression algorithm, and that's just kind of not true. And you'll see why. So why would you want to use this? There's packages like bzip2 if you want to compress a genome. Sites like NCBI Blast have a lot of data. They'd want to compress it. They'll use something like this for part of it. And it's used with stuff like bowtie and BWA for a long. So how does it work? So you start with a given string and you append a special character. I'm going to use a $sign for the presentation. You can use whatever you want. Point is, special character is not a letter, right? You want to generate cyclic rotations of the string. I'll show you what that means in a couple slides. You want to sort them alphabetically or lexicographically, same thing, just sounds fancier. Then you want to take the last column of the rotations. This is the BWT string. There's a BWT matrix, which is what you get when you sort everything, and then there's the last part, which is the BWT string. So what do I mean by cyclic rotations? As you can see, you're kind of cycling the special character back, and then the string follows. So you'll end up starting with, like, let's say banana, and you go down, and it's banana again, but this special symbol's at the end. And then you want to sort them alphabetically, which if you do that, you'll end up with this. And you see the BW2 string, ANNB $AA is the last column, the ANNB $AA. So what good is a compression algorithm if we can't reverse it? When we compress it and you want to like see what it is later on the other end, you want to be able to reverse it. So this is kind of the summary of how you do it. You construct the sorted matrix. You rebuild the string by iterating over the first and last columns, and then you extract the original string. This is kind of how it works. This is a different string. So you start with the BWT string that I mentioned earlier. You sort it, sort the two columns, and then you prepend the BWT string, and you repeat. So you start with the BWT matrix that has all the cyclic rotations of a particular string. You have the first column, which is, I'll denote as S from now on, is the letters of S of the string sorted alphabetically. And the last column, L, remember, that's a BWT string result, which is the last characters of each sort of rotation. So if you want to construct the matrix, again, this is kind of more of a formal representation of the example I had 2 slides ago, but you'd start off with the BWT string, and then you'd have the string at the next part of the rotation, and then you would keep iterating on it. You see, add another one. So you would repeat that O of n times to fully construct the matrix. So you want to know my mathematical complexity? Here it is. The reconstruction process takes O of n because that's just length of the string. Each iteration you need to sort, which worst case O n log n. Each comparison during sorting takes O of n time. So the overall complexity is O n cubed log n. That's not very efficient. I'm just trying to demonstrate Burrow-Wheeler transform. Its simplest case is there are optimizations. For example, there's one where you don't need the special character, but that would take a lot longer to explain, and you would need to understand this first one anyway. But point is, it's not very efficient. You can try to make this more efficient. This algorithm was made in the 70s. People have tried to make it more efficient. People haven't really succeeded, other than the people who figured out how to do it without taking the string out. So if you guys are good, you U of I computer science students, you probably, hopefully one of you guys figures this out and makes my life a little bit easier. Next section is brain imaging. I have some experience doing this while I was at the University of Wisconsin. It's not technically bioinformatics. If you look at brain imaging stuff, oh, sorry, what's on?
Maybe you don't do all. Okay. Go back to the property. Oh
yeah, sure.
I didn't quite. From here on, I didn't really quite follow.
Okay.
Yeah.
I think this is
Like a little more forward though.
sure. I'll just stick on this visual representation for now. I think this is the best one. So first you start with that last column. You'll have that here. And then next column over, you have a new column where you have a sorted version of it. So after you sort these, you sort everything else. So you want to sort everything lexigraphically. So you see you have the P's and the P's ending up together. And then you want to sort the BWT lexigraphically. And then you want to prepend it again. And then you want to sort it again. So it keeps repeating. And then eventually you end up with this BWT matrix. Does that make sense?
No, where are you getting?
Um, oh, so the next column would be this first column. So you're kind of like looping back around to the beginning. Yeah, it's cyclic. I probably should have emphasized that more. Does that make more sense?
Oh, you mean taking it all from
Matrix. Yeah, because you'd start off in a real life scenario, you'd have this matrix. And if you want to recover the original string from it, you would start from this matrix. So you would know these next successive columns. So brain imaging. This is technically more in the line of medical physics and not bioinformatics, but I think this is interesting. And I think there you learn some of this stuff in the computer vision course, but that's not 100%. I haven't taken the course. So I'll start off with active contour models. You'll also see these referred to as snakes. So why do we care about these? These are for image processing for object boundary detection. So you'd use these for edges. Snakes are curves that would evolve to minimize the energy function and capture object boundaries. So given an image's intensity in terms of brightness, a change in brightness would be an edge. So these are the edges that the snakes would look for. So we'll start, there's three different components. I'll go through them. First one is the line functional. Energy for line. I is intensity, X and Y are for a particular pixel on an image. So you want to see whether the snake is attracted to bright or dark areas. Basically, where's the edge? Sometimes you'll have a dark object on a light background or a light object on a dark background. These are kind of how MRI and other scans works. So it's going to be either one of those two. So you can apply the line functional as a filter. So that'll guide the snake towards the energy features that you're looking for in order to find edges. So here's an edge functional, and the edge functional will have the snake move towards the edges. So it'll move towards images of a high intensity gradient. So this is the Laplace. So, and you take the magnitude and then take the negative, and you eventually apply that using Gaussian smoothing. G sigma is a Gaussian function. I'm going to leave that as an exercise for the reader because it's a whole nother thing, and you'll figure it out if you ever do imaging. I think that's like the first thing you learn is the Gaussian function and how it's worked for smoothing. But you're basically just trying to make sure the image is smooth because you want a readable result at the end. That's kind of the important thing. And then this all comes back with you have the smooth image now from the line functional. And you have the line functional that defines where the edge goes. That's basically what this is doing. So you have those two. Oh, sorry. You have those two. You have the gradient angle, which is like the angle the gradient goes on the image. It's just making sure you have like a geometrically correct thing at the end of it. And then you eventually end up with the terminal functional, which is this is basically looking at like corners and sudden changes in direction. This is looking at curves and smoothing it, and then you're subtracting this term, which is like the light intensity, because the thing you're quote unquote afraid of is you don't want the snake to just be like, here, look where the light's changing. Here's where the intensity is changing. Because that's a big part of it, but that's not everything. So yeah, the total energy of for a given snake is the combination of all three of these. So you want to minimize this total energy because you want both smoothness and attraction image features because you want a readable image at the end. And usually we are working with a starting image that is kind of readable, but you want to improve it somewhat. So you have the line functional, which is the first part that guides the snake towards intensity regions, the edge functional that pulls the snake towards the edges, and then the termination functional, which captures corners and key feature terminations. So you want to conform to object boundaries, so you need to take all three of these into account. So here's a visual example of a snake from a paper from a UCLA in 1990, I believe. So in this painting of a pear, snake would latch on to where it sees a change in intensity, a change in gradient, and a change in the brightness. So all three of these see are like clearly defined as an edge. This is a very good image to use because it's very stark. But why would we care? This is a 3-month-old with severe hematomas. This part's unimportant. I mean, it's very important to the newborn. It's very unfortunate, but the reason where we care about this is you see this fuzziness. Some of you might be like, hey, I've taken an MRI. It looked a lot better. This MRI is trash. But the actuality is kids move a lot and they move during these MRIs. So the research I did at the University of Wisconsin was trying to smooth these out and get more clearly defined edges because we had a bunch of MRIs from kids who needed to be MRI'd. You can't really restrain their head while they're doing it, but they wouldn't stop moving. So you'd get a lot of this fuzziness. And kind of one of the only ways to fix this fuzziness in post processing is to use something like an ACM. So I'm going to move on. Oh, you have a question? It's kind of like a line that moves to the parts of the image that need smoothing based on those three functionals. Correct.
So the choice spelling, is it the connection?
Yeah, it'd be one part of a whole algorithm. It wouldn't be the whole thing. But that's one of the more basic ones. And I think it's one of the ones that has the greatest effect on an image because once you get a lot of the times the medically relevant information is in the edges. If you want to see like growth or atrophy, you'd probably want to look at the edges. So I want to go over k-means clustering. This is used in statistics a lot, but you can also use it for MRIs. So here's how you use an MRI. It can help separate tumor tissue from healthy brain tissue by clustering pixel on the intensity. So let's say you're an adult, you had a great looking MRI, but tumors a lot of the times look a lot like healthy brain tissue. So how would you determine what's a tumor and what's not? You'd want to look at each pixel by pixel basis and seeing how it differs in intensity, because a tumor would look different, but only slightly from brain tissue. Doctors used to have to do this by their eyes, and it was clearly not working great. So having a computer work out those intensities is very nice. Again, different tissue types. You can distinguish them much easier. Gray matter, white matter, supraspinal fluid, all in the brain, if you're doing a whole scan, can look very similar. And you can also use it for organ segmentation. I had to do this to rats that we gave very bad inflammation in their intestines. So we had to use k-means segmentation to segment organs. Because when you scan a rat pup that's 3 days old, you're kind of scanning everything, but we only want to look at the intestines, so we use this. So why does it work in MRI segmentation? So it takes the intensities, pixel intensities, it clusters them, things with similar intensities would be clustered together as being a X type of tissue or Y type of tissue, even if they're far apart. And it'll highlight the areas of interest that you need to look at depending on the parameters you set for it. So the reason I want to go over this is I want to look at the greedy algorithm for it, just so you get a very basic idea. There's obviously better versions of this algorithm, but I think this one is a good one to learn about k-means clustering. So you'll start with an arbitrary partition P in a K clusters, then you go until it stops. Set a best change for every cluster C, for every element that's not in C, you would evaluate it, and then you would either add it to I or C. And if best change is greater than 0, you'll change the partition. So I know I ran through that fast. I'm going to explain it. So first, you want to start with an arbitrary partition of P of the data in the K clusters. You don't really know how many clusters yet. There could be a lot of different tissue types. So you'll initialize a variable called best change that'll track the maximum improvement when you reassign points. And for each cluster C, you want to evaluate the quote unquote cost impact of moving each element I that's not C already that's into C. So you want to see how different is it for a given cluster to move a particular point into it. So that will get you similar clusters because you're evaluating, hey, how similar is each pixel? So you'll update I star and C star to the element, and you'll want to maximize its best change because then you'll get the most similar stuff together. So the best change in cost is positive. You'll reassign it because it's clearly not in the right cluster. And if there is a positive cost reduction at the end, it'll return the partition. We're like, hey, finally, we got everything that's similar. Everything that's not similar is too much cost to move it, so we won't move it. So you repeat that for each cluster until you don't see any more cost improvements. You guys have any questions about anything in the last slides or just anything in general?
So just to try to understand, if the k-means doesn't care about where they are, it just gives us some. Right? So if you have like a bunch of stuff on the edge, these various and what it still clusters those that's separated based on how intense. Right?
Yeah, because you'll have gray matter all around the brain mixed with like cerebral spinal fluid. So you don't want to just like group things that are in similar areas. That's nice if you're doing organ segmentation. But even then, like for stuff like rat pups, it's kind of everything is everywhere. So you want to be able to have something that can cluster, not based off just position, but more just based off intensity.
So if you cared about position, k-means.
You could combine k-means with something that could handle positioning, but yeah, no, it doesn't care about position. Wait, say that again? That's just like I would say it's a very simplified version, but it would basically you'd want to look at the how much would it affect the like accumulation of a cluster of points if you were to move it. So compared to all the points that are in a cluster, if you were to move a point and seeing how different it is, that delta is kind of what it's looking at, and that's the cost of moving something.
How do you determine what
It would do it randomly at first. It would just kind of group things arbitrarily, and as it keeps going, it would keep sorting. I probably should have included a visual representation of the algorithm because they're out there. I should have included it because I think seeing this visually is probably better. But if you have everything in separate points, slowly but surely you would sort similar stuff by looking about how much would it move based on there are yeah, I guess that's a good question, but that's why that's the greedy algorithm. It takes forever because it has all the points unsorted originally. If you were to sort the points beforehand, and then you would see, okay, from the stuff within this, there's clearly some stuff that doesn't belong, then viewing the cost would make more sense. No. All right. Hmm?
And then you do the algorithm. So
Yeah. Yeah, it'd probably help if you started with like something for positioning and then yeah, these are very small parts. If you're using like a whole image segmentation pipeline, it would be a lot of the stuff combined. So. Oh no, you guys end with a brain teaser. So you can, I would recommend trying to do each of these is a Smith Wasserman algorithm. You can try to do it yourself. I think it's kind of like doing Sudoku. I enjoyed doing this assignment a lot. But if you remember the rules I said before, you want to see like these three previous, and you can just fill it out. I feel like it's a lot more. I'm sorry, it's not probably not as challenging as the other brain teasers that you guys usually put. I was like looking at the brain teasers channel and I trying to solve some of them, and it didn't work. But I think you guys will have more fruitful success with this one.
Cool.